in order to identify these waste, we use non-destructive testing, and then we follow the dismantling and separation steps in order to have the parts and investigate if they are good for repairing or for recycling. So we use a smart sorting system with entity testing in order to identify the components and what are the substances in these components, in order to drive them either for recycling through different solvolysis approaches, either with sub and supercritical water solvolysis, or with chemical assisted solvolysis, or with plasma enhanced solvolysis. With this solvolysis technique, what we are trying to do is to recover actually the fibers included in these composites and drive them to the second generation demonstrators, which are automotive parts or all other construction parts, as for example, the container pontoon. So these are the remanufacturing approaches, and we use techniques like filament winding, compression molding, additive manufacturing, or conventional techniques as infusion to use the secondary products that come after the recycling of the parts. The other approach is to try to repair after the separation stage, to repair the parts with soft patches made by 3D printing for infusion, and to reuse these demonstrators as high-end products in the same application as the original part. So as mentioned before, we use the 6R strategy. So we would like to structure our project in a manner that the R6 strategy is being implemented. So we see here that the core of the project is, of course, the manufacturing and recycling technologies. Each of the work packages of EURECOMP is feeding the one work package the other. So starting with the first work package, where we have the waste streams technical monitoring, we proceed to the second one, where we have the separation and decision making for the different demonstrators. Either this will be the circularity by repurposing and repairing, or the circularity by recycling and reclaiming the secondary raw materials. This will fit work package 5, where we will have the advanced manufacturing technologies in order to manufacture new parts and for new applications. All these are being covered by work package 6, 7, 8, and 9, which refer to the safety, environmental, and performance, to the standardization policies and exploitation, and of course the management of the whole project. So starting with the first work package, which is the R6 strategy for waste streams management, we have objectives such as the circular design strategies with increased product durability. Here you may see that we investigate the whole life cycle of the project, of a product, from the material production till the end of life. So we see that the different strategies, the recycling, remanufacturing, repurposing, and refurbish can lead to a new operation of a part, or we can have repairing technologies for a closed loop recycling. In parallel, we have investigated stakeholders for new commercial possibilities and business opportunities. We have networked with other clusters, networks, and projects, and established a waste management system where we seek what can be the new applications for the repurposed parts. Either these are structural or non-structural applications. Here you may see a few examples. And while proceeding in the next, we see that the whole project targets to have a decision repurpose application approach. So we start with the end-of-life composites that should be reused. We screen the available materials, document the screen materials, and afterwards we see if, after inspection, if we have a small or moderate damage in order to decide what will be the next steps of the repurposing strategy. In this strategy, we follow principles for large-scale composites, such as the eco-friendly manufacturing, where we implement eco-friendly practices for the manufacturing that will be selected in order to reduce waste and energy consumption. Modular construction, which is the design of large composite structures in modular sections that can be easily replaced or upgraded individually, reducing the need for complete replacement. The design of durability or adaptive design that allows large composites to adapt to changing conditions and reducing the need of replacement. And the repairability, where we will design composite structures with easily accessible components that allow the easy and cost-effective repair. Last but not least, we would like to have a material traceability. That's why, in collaboration with Circularize, we will have a platform where we will trace the materials from their starting of their dismantling till the new component, and all recycling materials that will be integrated in the new demonstrator. Moving the next, we have the separation decision-making tool for demonstrators that will be the first generation demos of EURECOMP project, where the objectives here is to design a system for tracking quality and quantity of the disassembled and separated multi-materials. And this will be demonstrated through an intelligent sorting system, where the waste will be separated according to the specifications of the recycling technologies. So in order to implement this strategy, we start from the end-of-life carbon fiber reinforced and glass fiber reinforced parts. We check their quality, define the requirements for reusing, identify the materials, for example, with LIBS technology, dismantle and separate the parts, and afterwards repair, reuse, or repurpose the parts that have been selected. Here you may see a non-destructive technology technique used within EURECOMP project in order to identify probable flaws on the composite part. So the whole strategy and the decision tool is being presented here. Either if we start from aircraft or from wind turbine blade parts, we will use NDT or mechanical testing for the quality checking of the end-of-life parts. NDT actually refers to active thermography and phased array that are being carried out in EURECOMP project. And then we have the dismantling and separation strategies that lead us either on the recycling route or on the repair, reusing, and repurposing route. Of course, the materials need to be identified, and this can be done either with LIBS, as mentioned before, or with hyperspectral imaging in order to define the requirements for reusing. In order to proceed to a new component or a new application, we would like to assess the repairing technologies and to design new demonstrators for the prevention and reduction of waste with advanced modeling strategies for their evaluation and validation. So here you see an example of the first EURECOMP demonstrator, the first generation demonstrator that has been designed from HTWK and INEGI, and it's a floating a photovoltaic system. And here you may see that this is a small scale demonstrator and that being tested in real conditions and has been made up with a large composite part from a wind blade. In work package 4, we investigate solvolysis processes for the circularity by recycling and reclamation of the secondary raw materials. So actually here we have different solvolysis processes that are being investigated and upscaled. We try to compare the results of these processes and to proceed with an upscale of the most promising one. So starting, for example, with a low-scale chemical solvolysis from the Silesian University of Technology, we can gain the basic knowledge for the process optimization. Here, low molecular weight solvents and subcritical water are being used, and as fiber output we have batch fiber portions. Then we have the plasma enhanced solvolysis by University of Patras, where we combine plasma and organic solvent with oxidizing agents, and this is the process that can help us to retrieve continuous fibers to be used afterwards, for example, in filament winding or in continuous fiber 3D printing. You see results from a bobbin here that has been retrieved from a cylinder produced by BNT Composites, and this was chemically recycled with plasma enhanced solvolysis. And you see that we can have continuous and short also fibers. We have also the supercritical water solvolysis, which has started from TRL4. This uses sub and supercritical water with a fiber output of tapes or fabric patches of 50 square centimeters, and can be applied in compression molding, injection molding, or tape processing from the Technical University of Dresden. And finally, the chemical assisted solvolysis from Fraunhofer Institution in Germany, which will be select the most promising conditions from the previous techniques in order to upscale them in a 100-liter reactor, able to retrieve both chopped and continuous carbon fibers. So the targets here is to optimize the solvolysis conditions for fiber and matrix separation, produce high-value long fibers for textile fabrics and continuous yarns, and recirculate the waste material streams with fractional fractionation of dissolved matrix and solvents. The whole processes are being assisted by the simulation in order to find the optimum conditions. But the question here is, what are we going to do with all the waste that will come from these solvolysis processes, since we want to have closed loop recycling and to avoid having new waste from these processes? So here you see that if we start from a CFRP and try to recycle through solvolysis, of course we can get the reclaimed carbon fibers. And then we have the waste, the solvolysis waste, which consists from monomer and solvents. So what we aim to do within EURECOMP in NTUA is to synthesize carbon nanomaterials, for example, carbon nanotubes, from these solvolysis waste, and use them in combination with the reclaimed carbon fibers in order to size the reclaimed fibers with the nanotubes produced by the waste, and then have nano-enhanced CFRPs after using these new sized carbon fibers in the new composite parts. So the advantages here is that we can exploit the solvolysis waste, which is the major issue of the recycling process. We can synthesize high added value nanomaterials like carbon nanotubes from these waste streams and enhance the reclaimed carbon fibers for properties improvement in the new nano-enhanced CFRPs that will be produced by the recycled materials. By this, we ensure the circularity in the composite value chain. How can this be implemented? So we've noticed that we have various precursors that can be used for a chemical vapor deposition reaction. For example, we can have either gaseous precursors like methane, ethane, and acetylene, but also we can have liquid precursors, either type 1, which work on high decomposition temperatures, or the type 2, which can work on low decomposition temperatures. These are, for example, acetone, ethanol, ethylene glycol, and butanol. And we have noticed that the resulting liquid waste byproducts from a CFRP solvolysis process contains a mixture of water, in the case of supercritical water treatment, and organics from the depolymerization of the thermoset resin, which are monomers and the extra reactive solvent. And the solvent in this case could be one of these four solvents, organic solvents of the type 2 CNT precursors. So by combining the monomers, the organic solvents and catalysts, we can produce through the chemical vapor deposition reaction carbon nanostructures, either vertically aligned or in an entangled form. And so in NTUA, we have designed and assemble a chemical vapor deposition system in which we can introduce this solvolysis waste either through separation funnels or with conical flasks or with boiling on a 2-neck spherical flask in order to introduce this waste in the reactor. By this, we will be able to produce carbon nanotubes and carbon nanofibers that can be used in the sizing of the reclaimed carbon fibers. So the question is, what are we going to do with these reclaimed materials? So work package 4 fits actually work package 5, where in which different advanced manufacturing technologies are being investigated for the construction of the second generation demonstrators of EURECOMP project. So we have 4 different manufacturing techniques, either conventional or more advanced. For example, the filament winding, from which we will have an automotive shaft, compression molding, where we can build a formula seat, 3D printing, where we can design a steering wheel for a formula, and last but not least, the conventional vacuum infusion, with which a container pontoon will be manufactured. All these activities are being covered by the umbrella of safety, environment, and performance. So we have our package 6, which objectives are the cost evaluation, the assessment of the whole life cycle, and the risk assessment of the innovative processes in order to be aligned with the Safe by Design guidelines. So here we try to combine the functionality criteria with the safety profiles and the sustainability criteria, starting with the design and functionality of the new components and trying to combine with the safety, both in process level, manufacturing level, and use level. And lastly, to conclude to environmental and economic sustainability of the new parts that will be manufactured within EURECOMP. EURECOMP project also focuses on the training and lifelong learning. So we have started with the modular training concept, depending on the technical and qualification level from early career postgraduate students and workers on the composite industry. So at the end of the project, we will have an online educational program that can be available for all the stakeholders. But in parallel, we are organized each year open workshops, which can be attended by all people that are interested on the composite manufacturing technologies and the recycling technologies of EURECOMP project. So the next workshop is on April, on the 24th of April, where we will engage, learn, and connect with the reuse and repurposing strategies, with NDT technologies and recycling technologies on composites, with practical demonstrators. The second EURECOMP workshop will be held in Vigo, Spain, hosted by AIMEN partner. Also, we would like to invite you to a special session entitled Advancements in Manufacturing Lightweight Structures, which will be organized by NTUA during the 21st International Conference on Manufacturing Research that will be held in Glasgow in Scotland in August, from 28th till the 30th of August. The abstract submission deadline is on March 30, and in case you are interested to submit a work in this conference and this special session, please inform us till the 15th of March. This action is within the communication, dissemination, and exploitation activities of the EURECOMP project, where we're trying to strengthen the European industrial base and boost its competitiveness and open strategy autonomy. Also, I would like to invite you to a special issue that is being edited by Professor Kostas Charitidis and myself, which is the Smart and Intelligent Composite Structures for Innovative Industrial and Space Applications for Fiber Reinforced Polymer Composites in the Polymer Journal. The scope of this special issue is the synergetic effect of nanomaterials in reinforcing fiber-based composite materials, the smart polymeric nanocomposites, novel processing technologies for fiber-based composites, smart functionalities of fiber-reinforced composites, multifunctional fiber-based polymer composites, modeling and simulation for fiber-reinforced polymer composites, and their recycling. By this, I complete the first EURECOMP webinar from a series of 4 webinars planned within 2024. The next webinar will be the dismantling aircraft composite assemblies for recycling according to aviation regulations, delivered by Alexander Knorr from EFW in the mid of June, and 2 other webinars will follow by the end of September and early December in 2024 by AIMEN, INEGI, and ITAINNOVA partners of EURECOMP project. I would like to thank the whole NTUA team for the achievements of EURECOMP project till now, Professor Kostas Charitidis and Eunice Simtekoulos, that we are together working in the management of the European project, as well as my colleagues in the technical implementation of the project, working with extrusion, 3D printing, sizing, recycling, and chemical vapor deposition. Thank you very much for your attention, and I'm open to your questions. From Maria Modesto.
Hello, Kate. I would like to ask how efficient are the chemical recyclings of the partners within the EURECOMP project?
Okay, so as you notice, we have different approaches. The efficacy can be considered in 2 ways. If the fibers that are being reclaimed are clean and robust and can be used in the new applications, this is one criteria. The second is the efficacy in terms of the amount of recycled materials that can be obtained through a process. And the third one is the economical viability of this. So, for example, if I can take one by one, the Silesian sulfolysis is efficient, but it's not upscaled. So we can work up to a 1 liter reactor. So we cannot upscale this without a new design of a new reactor. That's why we have Fraunhofer, which can use the solvents and conditions of SUT and upscale the whole process up to 100 or 200 liter reactor with the output of 100 of kilos within a month. As for the plasma-enhanced solvolysis, which is the most innovative solvolysis process of the EURECOMP project, we have a very nice recovery of carbon fibers in continuous form, but we have limitations due to the dimensions of this reactor. So what EURECOMP plans actually is to combine the condition of SUT with the mechanism of retrieving continuous fiber from University of Patras and Fraunhofer to combine these 2 technologies in order to retrieve the continuous fibers. As for the economic viability, this is a general question for all recycling technologies used for composite materials, because the truth is that if we invest in this type of technologies, we use energy, we use solvents, we have new ways, as mentioned in my presentation. So we need to balance the cost of making a new raw material and the cost of recycling a material through this type of process. And this depends, of course, on the application. I don't know if I answered to your question.
Thank you very much for your answer, Kate.
Thank you too. Other questions? Yes, there's a question from Stefania Termine.
Yes, hello. Thank you, Kate, for the very informative presentation. My question is a little bit related to the previous question regarding the extraction of the carbon fibers, but with regards to the valorization of the solvolysis byproducts. You have mentioned that there will be applied sizing with nanomaterials on the carbon fibers. So in this case, these carbon fibers are nano-enhanced sized and will be applied to all the demonstrators of EURECOMP project, or will be some sorting for the properties that you want, so different demonstrators will have, let's say, other type of sizing, or everything will be with nanomaterial sized fibers?
Actually, in EURECOMP project, we have two types of demonstrators that will be built with the continuous fiber. The one is automotive shaft that will be prepared by BNT Composites through filament winding, and the other one is a steering wheel that will be manufactured through 3D printing by BioG3D for Dallara. These two manufacturing techniques will use the reclaimed continuous fibers, in which the sizing, the appropriate sizing, first of all, will be applied by NGUA. And when I'm talking about appropriate sizing, this needs to be combined with the polymer matrix of these components. So for the first case, where we have the automotive shaft, it will be a thermoset resin used for the filament winding. So here we will have conventional sizing of the reclaimed fibers, in which we can use the carbon nanotubes that will be produced from the solvolysis waste. This is the most easy way to reuse these carbon nanotubes and to enhance the mechanical properties of the composite that will be produced. For the second approach, where we'll have the steering wheel, due to the fact that a polyamide will be used as a matrix material, we are investigating the sizing of the reclaimed fibers through a thermoplastic sizing solution. So in this case, we have not proceeded yet with the incorporation of the carbon nanotubes that will be produced from the solvolysis waste through chemical vapor deposition, since we are still on the investigation of the application of this thermoplastic sizing on the fibers.
Okay, thank you very much for your answer.
Thank you too. Other questions? Haris, I don't know how you would like to proceed.
Okay. Thank you very much, Kate. That was a very enlightening first webinar for our series. Thank you very much, everybody, for attending this webinar, and stay tuned for more webinars to come, as already mentioned by Kate. Thank you very much, everybody.